Welcome back, everybody. In today's tutorial, we're going to do something that seems really smart on the surface, but in the end turns out to be really quite dumb. We're going to try to add experience replay to an actor critic network and see how it works. Let's get to it. Now, this project was motivated by my experience doing research in physics. So in physics, we would say, what happens if we combine two really good ideas? Or, hey, if X is true, then Y should also be true. Let's design an experiment to see what happens. Now, 80% of the time, this didn't work, and that's just kind of the way the research game is played. Not all your ideas are going to work, but the times that they do work, it pays off big, and you're winning. So I haven't done any real original deep learning research, but I imagine it's probably a fairly similar process where people are sitting around saying, hey, you know, this idea is really good. What happens if we apply it to this other thing where we had some success? And sometimes it works, sometimes it doesn't. And this is one example of this, and the reasons why will become more apparent as time goes on, particularly if you've taken my course on deep Q learning, which, by the way, on Cyber Monday today is for sale. Go ahead and check it out up through the 4th. All right, so let's go ahead and get started, though. Let's start with our imports. Torch st for our base pytorch package. Torch.nn for our linear layers. nn.functional for our activation functions. Of course, our optimizer. And NumPy to handle NumPy type operations. Now, an actor critic network is a little bit different beast than the value-based methods like deep Q learning. So we're still going to have a replay buffer because that's kind of what we're doing this project for. The replay buffer will be a little bit different. Instead of saving the actions, we're going to save the log probabilities of those actions because it is the log probability that goes into the update rule rather than the actions themselves. So our initializer should again take the max size and input shape as inputs. The memory counter gets initialized as 0, so there are many ways to handle a replay memory. I do it with specifically enumerated NumPy arrays. You can do it with a DQ, which is basically a Python linked list where you append stuff to the end and pop it off the front. But the disadvantage there is that you have to dereference the objects that you pop off because they decompile into 5 NumPy arrays anyway, so why not just save 5 NumPy arrays to begin with? And when you're saving an array, you want to make sure that you know the position of the last saved memory, and that's what the mem counter is for. So our first quantity is the state memory, and this will handle the memory of the observations from the environment. We do have to know the resulting states, so we do also have a new state memory, which would be, you know, pretty familiar to you if you know something about deep Q learning, and it's otherwise identical in terms of shape. Other thing we need is the log prob memory. And that is mem size shape and a NumPy float 32. This handles the memory of the log probabilities of the actions, which goes into the update rule. Let's scroll down so you can see. Next, we need a reward and terminal memory. Now, the reward memory is precisely as the name suggests. It is the memory of the rewards the agent receives, and we will use that to update its estimates of total future returns following a given state. The terminal memory handles the fact that the updates that the value of the terminal state is 0, and so we need some way of keeping track of which states were terminal. Next, we need a function to store transitions. And that'll take the relevant quantities as input. And the first thing we want to know is what is the index of the first available memory. That is given by the modulus of the memory counter with the memory size, and this has a property that when the memory counter exceeds the memory size, it will just loop back to the beginning and start overriding the original memories. And then you just want to save the relevant parameters at that index position in their respective array. Equals done, and I've forgotten my indexing, and I'm screwing this up so badly because as I'm reading it I realize I misspelled terminal up here. Terminal, there we go. All right, and then the next thing we want to do is increment our memory counter by 1 because we've just stored a new memory. So the next thing we want to handle is sampling the memories, and this is actually where part of the problem of this approach comes in. So we are going to use a uniform sampling, and this actually turns out to be bad. This is kind of where the approach breaks. And if you read the paper on Acer, which is Actor Critic with Experience Replay, they use something called importance sampling, but we're going to use a naive implementation, just kind of a stupid, hey, why don't we just apply what worked in DPQ learning to Actor Critic methods and see what happens. So we have our sample buffer function, and that takes a batch size as input. The thing we want to know here is what is the integer index of the last stored memory. So we only want to sample memories that we've actually written. We don't want to sample a bunch of zeros. So we have to know what is the minimum of either the mem size or the memory counter. Self dot. And then we want to perform a NumPy random choice on 0 to that number and batch size shape. Now this replace equals false. This has the functionality that when an integer is drawn from that range, it will not be placed back in the pool of integers to be drawn again, so we can't resample memories more than once. Then we simply want to sample the arrays for those batch indices. We need states underscore and the dones. And of course you want to return everything that you sample. So that is it for our replay buffer class. Now we can handle the question of the Actor Critic network itself. So there are a couple ways of handling this. You can have an Actor Critic network where you have separate lower layers. In other words, two totally separate actor and critic networks for learning the environment, or in this case, we're going to have common lower layers that splits into two streams, which are the policy and value functions. So let's start writing our class. And as is the case with PyTorch, we always want to derive our network classes from nn.module. This will take a learning rate, input dims, FC1 dims, dims for the first fully connected layer, and dims for the second fully connected layer, and number of actions as input. And we want to call this super constructor. All right, let's scroll up for you guys, and then we want to start saving our member variables. Next, we want to start constructing our actual network. and this will be a sequence of linear layers that goes from the input dims all the way to the number of actions out for the policy and a single value for the value function. Whoops, FC1 dims. So if you're not familiar with reinforcement learning, the policy is a mapping between states and the probability of selecting actions. In something like Q-learning, we are approximating the value of each action given we're in some set of states, and then we use that to compute the greedy portion of an epsilon greedy action selection policy. In actor-critic methods, we want to model the policy itself directly, and so we're, instead of having epsilon greedy action selection, we're going to model the probability distribution by which the agent selects actions, and then use that probability distribution to actually select actions. Next, we need our value function. And so this corresponds to the value of a particular action given some set of states. Now, just a word on nomenclature. This is our actor because it tells us what to do, and this is our critic because it tells us, like a critic does, the value of what we actually did. It says, hey, what you did was stupid, maybe you should try again. That's it for our network. The next thing we need is an optimizer. And we'll use the atom optimizer, a stochastic gradient descent with momentum and variable learning rates, with a learning rate defined by LR. And what are we going to optimize? We're going to optimize the self-dot parameters, which is the parameters of our deep neural network. Where do we get that? That comes from the derivation from nn.module. That's why we do that. Next thing to worry about is the device. So if you have a GPU, you really want to use it. And so this will handle device selection for you. If you have a GPU, it'll select it. Otherwise, it'll select CPU. If you have more than one, I believe you can do CUDA:1. Though I haven't experimented with that directly, I always send networks to the GPU using a different method with the OS environment variables. But anyway, finally, you want to send your network to the device. And so that wraps up the constructor for the actor-critic network. Now we have to handle the feed-forward function. So in other words, how does it turn states into pi and v? And this takes a state as input. And we've assumed that the state is not a NumPy array, but it is already a pytorch tensor. So when we go to pass states to our network, we have to do that first. This doesn't perform that operation for us. So we pass it through the first fully connected layer and activate it with a ReLU output. Then we pass the output of the first fully connected layer through the second fully connected layer and activate it again. Then we're going to take that output and feed it simultaneously into our pi and v networks and then return both. And notice we don't activate those because we want them to have whatever value they come out as. All right, so that handles our actor-critic network class. Now let's deal with the agent class. So our agent is really going to tie everything together. It's going to tie the memory, network, and action selection and learning functionality together. So let's code that. So it takes a learning rate, input dims, number of actions, a gamma, which is our reward discount factor, network sizes, batch size, and memory size as input. 256, batch size 32, mem size 1,000,000 memories. And this 1,000,000 memories, which you can't really see, is only good for environments with small observation variables. If you have, like say, the Atari library, then you definitely don't want to do the mem size of 1,000,000 because you're going to run out of RAM almost certainly, unless you're running on a pretty beefy workstation. So let's go ahead and save our member variables. And instantiate our memory. Instantiate our actor Critic network. All right, so that wraps up the initializer. Let's go ahead and handle the store transition functionality. And this is literally just an interface function between the agent and its memory. All right, let's scroll down a little bit. Next thing we need is our functionality to choose an action. Now remember, this isn't epsilon greedy action selection, so we're not, selecting any random numbers from the uniform distribution. And that takes an observation of the environment as input. So the first thing we want to do is turn that observation into a pytorch tensor. And we enclose it in a list to handle the dimensionality problem. So we want to be able to simultaneously pass in both single observations as well as batches. So we're going to pass in everything as a batch, but create a batch of one by creating a list out of it. And the lowercase t will preserve the data type of the underlying NumPy array, which is the behavior we want. And we want to make sure to send that to our device. Next, we have to pass this through our network and get our probabilities and values out. We don't care about the values, so we just use an underscore. Dot forward. Sorry. Next, we want to normalize the probabilities using the softmax function. So I guess here calling this probabilities is a bit of a misnomer because it can be a negative value, which obviously doesn't correspond to any probability in this universe. But the quantity here is certainly a probability because they are all positive definite and add up to 1. Next, we want to know what the next we want to actually get probabilities out from a distribution using that set of numbers. And categorical is just a distribution that deals with an object that has a discrete number of classes, a discrete number of categories. Then we want to sample that distribution to get our actual action probability, meaning the set of n actions probabilities. And then we want to take the log of that. Because we need that for the calculation of our loss function. And then we want to return not just the action, but also the probability, the log probs of that as well. And we get the action through dereferencing with the .item function and our log probs. Okay, so next we turn our attention to the alerting functionality. So this function doesn't take any inputs because we're going to be sampling our memory. If you see my other videos on Actor Critic, we usually pass in, a state action reward pair, but we don't have to do that here because we're using a memory. But we do have a question to deal with straight away. So that question is, what do we do if we haven't filled up the batch size of memories? So the way we have it set up with a replace equals false, it'll actually throw an error if you try to do a sample before you filled up enough memories, but we should be a little bit more robust with our code. So let's say if we haven't filled up batch size of memories, we just return. So we don't try to learn from zeros, we just get the heck out of there and keep playing until we have enough memories to actually learn something. And as usual in PyTorch, at the top of your learning function, you want to zero the gradients. Scroll down a little bit. Then we want to sample our memory. And then we have to turn those into PyTorch tensors. So we're going to write this over and over again. Let's just go ahead and copy that. Probs, rewards, rewards. And dones. That is done. And new states. Okay, so we have sampled our memory. The next thing we have to do is perform the feed forward operations to get our critic values out. And we do that for the next states as well. So that tells us the values of the current state and next states as according to the critic network. Next thing we want to do is set the values for the next states where they are done equal to 0. Next thing we want to calculate is what I call the delta, and that is rewards plus the gamma times that critic value underscore. And this is very similar to the update rule for Q-learning, so this should be no surprise if you've seen those videos on this channel. Next thing we need is the actor loss function, and that's given by minus t.mean of probs multiplied by delta minus critic value. So what we've done here is we're multiplying the probabilities of selecting an action by the difference between the maximal should be a minus, not an underscore, multiplied by the difference between this delta, which is the maximal value for the next state, minus the value of the current state. So we want to move the probabilities in the direction of the quantity that minimizes this value because we have the minus sign out front. So we're going to want to minimize this. And what are we minimizing? We're minimizing this quantity here, which is the probability of selecting actions that are suboptimal. So we're trying to minimize the probability of selecting suboptimal actions. It's kind of the intuitive explanation for it. But we also have a critic loss, right? Because we have, two portions of our network. So critic loss equals a mean squared error loss. And this is very similar to the Q-learning algorithm. And that is between delta and critic value. So we're going to take the mean squared error, so delta minus critic value quantity squared, divided by number of batch size. And then we want to sum those two losses and backpropagate. And step our optimizer. And save. So the one thing to note here is if you're getting an error where PyTorch barks at you and says that grad can only be cast implicitly for scalars, it means that you're trying to calculate a loss on a vector quantity, an array, instead of a scalar. And so to deal with that, you need a mean function here. So if you don't have this mean function, then it'll give you that error. All right, so let's go ahead and code up our main function and see how it all does. All right, so we start with our imports. We need Jim for the Lunar Lander, NumPy to handle the mean operations to plot or to print the mean scores to the terminal. We need our agent and our plot learning function. Let's make our environment. Set our number of games. In this case, I'm going to go with 1500. It's not really necessary to go to 1500 because it doesn't work, as I stated in the introduction. This is something that seems like it should, but does not actually work. You can let it run from now until eternity, and you're not going to see any actual evidence of learning. But we'll go with 1500 games. And spoiler alert, I'm not going to let it run all 1500 games because I've already shown you the learning plots. We already know it doesn't work. This is just showing you why, and I'll get to why at the end. Let's instantiate our agent. A gamma of 0.99, a learning rate of, it doesn't really matter, we'll say 1e to the minus 4. And I have played with different parameters, and in several different instances it doesn't actually work, so I'm pretty confident that it doesn't work. And also people came up with a whole paper called Acer, Actor Critic with Experience Replay, where they do a far more sophisticated approach, so that tells me that, yeah, this is a dumb approach and it doesn't work, but for interesting reasons. And it also tells me that, it tells me that no other selection of hyperparameters is going to make the thing work. So 4 actions for the Lunar Lander. We'll start with an L1 and L2 size of 256. Again, doesn't really matter because I've played with a fairly broad array of hyperparameters and can't get this stupid thing to work. Now, if you fork this and get it to work, by all means, I'll go ahead and drop a pin comment and said, hey, for this one special use case, someone managed to get it to work. But that only proves that the technique is really not robust. If you have to do extreme hyperparameter tuning, if a whole crowd of people have to do hyperparameter tuning, then it's not really robust. It doesn't change the heart of the conclusion, just changes, just provides a simple corner case exception. And a file name, an array to keep track of the scores, or a list rather to keep track of scores. Let's iterate over a number of games. And for each game, what we want to do is select an action. Scroll down a little bit. Go ahead and take our action. Increment the score by reward. Store our transition. Correctly spelling observation. And our done flag. Perform our learn operation. And set the old state to new state. At the end of the episode, we want to save our score. Calculate the average for debug purposes. And print a debug statement to the terminal. And then finally, at the end of all the games, we want to do our plotting. Let me scroll down for you. All right, hit save and go ahead and run our games. Let's go to the terminal and see how it does. All right, let's go ahead and give it a try. Okay, so I have a typo in my file here. Let's go ahead and fix that. So that should be over here in line 94. So I'm calling it here, and then it goes up to right here. Perfect. All right, let's head back to the terminal and see how many more typos there are. Once again. Name critic values underscore is not defined. Okay, that must be another typo. 1 second. Because I certainly meant to define it. Critic value. Oh, it's singular. All right. Perfect. Let's go back to the terminal once more. And it is running. Okay, so no matter how long we let this run, it's not actually going to learn. And even if I try a whole bunch of different parameters, it's not going to learn. So what is the reason? So let's back up for a second and think about what the purpose of the replay memory is, at least with respect to Q-learning. So in Q-learning, we need the replay memory because the agent samples a series of highly correlated states and state transitions. So if it finds itself on the left side of the screen, it's only going to sample states from the left side of the screen. This confines it to a very narrow portion of parameter space, and so it doesn't generalize well. So once it gets over to the right side of the parameters, right side of the screen, it doesn't have any parameters to deal with that, and so it sucks. The actor-critic methods have the exact opposite problem. So the problem that actor-critic methods have is that we're really dealing with two different spaces. So we have the parameter space of our deep neural network, and then we have the policy space. So small perturbations of the parameters of the deep neural network can result in larger movements in parameter space. So even if you do it well using the regular actor-critic methods without the, just using the single state transitions, you'll see that you get a big cliff in performance. And that's because it takes too large of a step in parameter space and goes off into la la land and doesn't know how to play. So what we're doing here when we're sampling a bunch of different parameters is we're jumping all over parameter space, causing significant jumps in policy space, so it can never actually learn. So it's the exact opposite reason of why the experience replay helps deep Q-learning. Too big of jumps in parameter space. So that's actually kind of an interesting phenomenon, and that is something that is handled in the ACER paper, actor-critic with experience replay. You need a far more sophisticated method of sampling your memories. And the other problem with taking too large of steps in parameter space in policy space is dealt with in algorithms like TRPO, Trust Region Policy Optimization, as well as PPO, Proximal Policy Optimization, which I will be making videos on that in the future. So I hope this was helpful. Make sure to like and subscribe, leave a comment down below, and hey, don't forget my course Deep Q-Learning from Paper to Code is still on sale for the next few days, so if you made it this far, please consider purchasing. I'll get it to you for $9.99, cheapest deal on Udemy. I look forward to seeing you in the next video.